Right, I think and hope this is where I was. Yeah, I got the 29 minutes and the camera stopped filming, and I noticed that and started again. And then the camera stopped again. So, hydrogen fuel cell and rechargeable lithium-ion batteries can be used to power electric cars is what I hope was coming next. Complete the balanced equation for the overall reaction in a hydrogen fuel cell for 2 marks. So, probably 1 mark for the equation and 1 mark for balancing it. Balancing it means you have the same amount of stuff on both sides of that. It's not an equals, it's a becomes symbol. Fuel, H2. 2 hydrogens, 1 electron from each, shared in the middle in the overlap of their 2 shells to form a molecule of molecular hydrogen. Output, H2O. 2 hydrogens and 1 oxygen as described. Water, or water vapour if it's burnt, because it's likely to come out kind of hot. The missing thing is oxygen. As we're talking about an air-breathing engine, it'll be breathing in air and using oxygen from air. Oxygen in air tends to be in molecular form, as also previously described, O2, like this, but O not H. So you put O2 in there, and you have hydrogen plus oxygen makes water. That's the equation for 1 mark, but they want it balanced. If you just do that, you have 2 oxygens here and only 1 here. So you need to add a big 2 here to double the water. So you have 2 H2O, which is great. You now have 2 oxygen there and 2 oxygen there. But that's 4 hydrogen, so you need to double this hydrogen here to have 4 hydrogen on the input side as well. So 2 H2 plus O2 to 2 H2O. Right. Table 1 shows data about different ways to power electric cars. Table 1 shows that a rechargeable lithium-ion battery takes 6 times as long to recharge as it takes to refuel a hydrogen fuel cell vehicle. In minutes, 30 and 5. That the hydrogen fuel cell vehicle can go, well, it's not twice, but it's almost 1 3/4 times as far between refuels as the lithium-ion battery vehicle goes between recharges, in miles, because we're in England and still use miles. Miles and yards on the roads and pints in the pubs. Everything else is in kilograms and meters and litres, but we still use miles on the road and pints in the pubs. That the rechargeable lithium-ion battery travels 3 times as many kilometres, because we don't use miles anymore because we're in Europe, as on the same amount of energy as the hydrogen fuel cell vehicle, making it 3 times as efficient. The hydrogen fuel cell vehicle costs almost 17 times as much to refuel as the lithium-ion battery takes to recharge, and the minimum cost of a hydrogen fuel cell car is more than 3 times the minimum cost of a lithium-ion battery car. So the greater distance between recharges is nice. You know, only 240 miles, you even at 70 miles per hour on the motorway, which is an inefficient speed and probably wouldn't get you 240 miles on one charge, because you have a lot of air resistance and you're losing a lot of energy just stirring the air going that fast. That's 3.5 hours. If you're going slower speeds, maybe 50, that's almost 5 hours. Even 3.5 hours, you should be stopping for a half-hour break anyway. So as long as there is somewhere to recharge your battery, stop, have a coffee, pee, wash your face, browse through the porn mags on the top shelf or something, I don't know, but take a break rather than trying to drive for 7 hours without a break and crashing and killing someone. Also, good grief, £42,000 is a lot of money. And if you're paying £50 per 400 miles, or paying £3 per 240 miles, You know, that's also a lot of money if you're doing a lot of miles here. This is going to add up. Also, you have to produce the energy somehow. Producing hydrogen for this thing costs energy. You have to extract it from seawater or something like that to get it, and that takes energy, which has to be generated somewhere. Just as this thing takes energy, it has to be generated somewhere. Either way, that energy generation is quite possibly damaging the environment, but it's 3 times as damaging if you're running on a hydrogen fuel cell. Use table 1 on your knowledge to compare rechargeable lithium-ion batteries and hydrogen fuel cells to power electric cars. All of previously stated things, and a lot of lithium comes from China. A lot of power generation fuel and road vehicle fuel that is neither hydrogen nor lithium-ion batteries comes from the Middle East. That's where people are more happy about their money going. Oh, there is one other thing to consider, actually. Fairly serious consideration. A huge lithium-ion battery is a bit like an armoured vehicle sitting in the base of your car, but it's full of lithium. If it ruptures, you have this very reactive metal exposed, and that could get very exciting. A hydrogen fuel cell vehicle has to be carrying a big tank of hydrogen gas under pressure, and hydrogen leaks out. It's a very small molecule. It's notorious for being able to escape through rubber. You can't just pipe through a rubber hose, it leaks out through the rubber. Very difficult to contain, especially long term, and if it ruptures, you're spraying very flammable gas out under pressure. Now, it's very low density gas, it'll go upwards quite quickly, but first it's getting sprayed out inside a damaged vehicle which may well have exposed damaged electrics and hot engine parts. That's an interesting hazard to consider. You have all that room in which to write that down. Figure 3 represents different models of the atom. Figure 3 can sod right off. None of those is correct. Have a look at this. Grid pattern? I don't think so. Right. What they want is which is the plum pudding model, which has long since been rejected, so we no longer care which is the plum pudding model. Which diagram shows, in fact that was one of the examples of a rejected model that was replaced with a better model that was in one of the GCSE physics papers, wasn't it? Which diagram shows the model of the atom developed from the alpha particle scattering experiment? I don't care. Which diagram shows the model of the atom resulting from Bohr's work? Oh, I got bored halfway through hearing about it. I'm sorry. Right. E is just plain wrong. Although, there's a big cloud of negative charge, which is the electrons in general, with 4 positively charged protons bumping around in it. Now that's just wrong. That wouldn't explain ions properly, so reject E. Plum pudding, probably B, because you have the 4 electrons like bits of plum in a big pudding with a net positive charge. For a total of net 0 charge. And then one of these was produced by scattering alpha particles. Now an alpha particle is a helium nucleus, which is 2 protons and 2 neutrons, which is rather too big to resolve individual protons and neutrons. It would be deflected by both. I would guess thing is, these orbitals are a bit fancy, compared to these flat circles. If you're scattering something, you would be sending it from one side, as if looking at one side of a piece of paper. Maybe you would get A. How do I know? I'm guessing B for plum pudding, and okay, BCA. What the heck? I might be right. Define the mass number of an atom. It's only one mark. Total number of protons and neutrons in the nucleus. Element X, insert X-Men or Avengers theme music here, has 2 isotopes. Their mass numbers are 69 and 71. Right. Isotope is a different version of the same element. Same element means same number of protons. With a different mass number, it has to have a different number of neutrons. Percentage abundance of each isotope is 60% 69X. Nice. 40%, 71x. Estimate, not calculate, just estimate the relative atomic mass of element X. Your options are below 69.5, between 69.5 and 70, between 70 and 70.5, or above 70.5. In other words, is it going to be in the first, second, third or fourth quarter of the range from 69 to 71? Well, given that slightly more than half but less than 3/4 of it are lighter isotope, I'd guess the second one. You can actually work this out. How can you tell that I lost a recording? Because I already did work it out. 60%, also known as 0.6 of it, is 69, nice. And 40%, also known as 0.4, of 71 is 69.8, which is indeed in the second range there. Chadwick's experimental... Who the hell is Chadwick? Don't know the man. Well, you missed your chance because you shot him dead yesterday. Sorry. Chadwick's experimental work on the atom led to a better understanding of isotopes. That's nice. Explain how his work led to this understanding. I have no idea. This is a history question on a chemistry paper. A student investigated the temperature change in displacement reactions between metals and copper sulfate solution. Right, displacement reaction is the metal displacing the copper out of the copper sulfate. So you go from metal and copper sulfate to copper and metal sulfate. Very first one, copper. Right, your reaction is copper plus copper sulfate, arrow copper sulfate plus copper. No change. No change in any energy state, no change in total energy, no energy consumed or released, no temperature change, no surprise. Iron. Iron plus copper sulfate becoming iron sulfate plus copper plus 13 centigrade. You may recall from a physics paper that water has a specific heat capacity of 4,200 joules per kilogram degree C. Magnesium plus copper sulfate becoming magnesium sulfate plus copper, 43, more energy released. Therefore, there is a greater decrease in energy level, which means that the fact there's energy released at all means that the decrease in energy level from pure iron to iron sulfate is greater than the increase in energy level from copper sulfate to pure copper. That's why the reaction happens that way around. My copper wouldn't displace iron sulfate out of solution. Technically, but I don't think GCSE goes as far as equilibrium levels, so never mind. The fact that there's a greater change here means that there is a greater decrease in energy state from magnesium to magnesium sulfate than there is from iron to iron sulfate. Zinc also reacts and displaces the copper, releases more energy than iron did. Which is why you can put zinc on the outside of your boat near the propeller and prevent the propeller dissolving in the seawater, because the zinc dissolves instead. Plot the data from Table 2 on Figure 4 as a bar chart. Yeah. The student concluded that reactions between the metals and copper sulfate solution are endothermic. Give one reason why it is not correct. Because they're exothermic, which is the opposite of endothermic. They gave out heat, they didn't take it in. The temperature change depends on the reactivity of the metal. Yes, I just said that, didn't I? The student's results are used to place copper, iron, magnesium and zinc in order of their reactivity. Describe a method to find the position of an unknown metal in this reactivity series. Your method should give... Oh dear. Flat earthers, take note. Your method should give valid results. And they should be interesting. Okay. A method, a suggested method. You could try putting samples of the metal into samples of copper sulfate, iron sulfate, magnesium sulfate and zinc sulfate solutions and seeing which ones it displaces and which ones it doesn't. And if you can't tell visually, just see which ones get warm. Or you could do it vice versa. You could put copper into unknown metal sulfate, iron into unknown metal sulfate, and so on, and see which ones displace it. Or you could run... Actually, it might be worth doing both, just to confirm that it isn't copper. If you do it both ways round, if you only do it one way round, then it is one of them, it won't displace it. If you try to do it both ways round, and it's one of them, that one won't displace it either. So then you identify it rather than just saying it's less reactive than copper or more reactive than magnesium. You identify it as being, well, equal reactivity to copper or magnesium rather than necessarily being copper or magnesium, but I mean, what are the chances? Love it. Your method should give valid results. Yeah, you could also use a different metal. Silver nitrate. Try using it in a displacement reaction with silver nitrate. The problem with using silver nitrate, the stuff reacts to light. Decomposes when exposed to light. Draw a fully labelled reaction profile for the reaction in zinc and copper sulfate solution on figure 5. Zinc and copper sulfate have higher energy, so they would be somewhere up here. Copper and zinc sulfate have less energy than that, so you put them down here. In between, you would have this weird mid-energy state, which is, generally speaking, higher than both, so I would just do that. 3 marks. 1 for labelling the constituents there and there, 1 for that being higher than that, and 1 for the middle being higher than both. And if you want me to tell you what's actually there in the middle of that, you add a look. There are no questions printed on this page, so you lose no points for that page. A student investigated the electrolysis of different substances. Right, this is the opposite of the cell we had earlier. Instead of one of these dissolving and the other one collecting stuff, and that generating a current which runs through here, current running that way, electrons running that way. Instead we have a DC power supply driving electrons this way through the crucible of stuff and up like that, which means driving the current that way, because that guy called that charge negative that one time. Explain why electrolysis would not take place in the apparatus shown in figure 6, because the zinc chloride shown in figure 6 is labelled as solid. Generally speaking, stuff in a solid doesn't move around much. Yeah. Otherwise it would be called a liquid or a solution. Explain why graphite conducts electricity. Answer in terms of the structure and bonding of graphite. 3 marks. Graphite is pure carbon, not in diamond form. It's funny stuff, carbon. It takes all kinds of forms. You don't get a mark for calling it funny stuff, though. Graphite is a hexagonal grid pattern of carbon in each of multiple sheets. And instead of being... if you draw out a hexagonal grid, or you look up one that's used for a tabletop role-playing game, you'll see that each point, each junction point in that grid, only has 3 bonds. 3 lines coming out of it to the adjacent ones, not 4. Which, as previously discussed, carbon wants 4 bonds. Where's the 4th bond? Well, the 4th bond is diffuse. Instead of the electrons being in a particular bond, this bond is single, this one is single, this one is double, you have 3 single bonds and a whole load of electrons that are just shared across the whole layer of graphite. And those electrons are free to flow across it, which means it is possible for an electron flow through the graphite to happen, which means it is possible for electricity to flow through the graphite. A student investigated, I'm sick of reading, the student this time, it's the same one, investigated how the volume of gases produced changes with time in the electrolysis of sodium chloride solution. Oh boy. Figure 7 shows the apparatus. Sodium chloride solution is just salt water. But in our 2 inverted test tubes here, we have hydrogen gathering in one and chlorine gathering in the other. This is rather dangerous stuff. Anti-vaxxers, take note. Table salt, sodium chloride, contains chlorine. Really dangerous stuff. Yeah. Graphite electrodes, isn't it convenient that graphite conducts electricity? A thing kind of like a bottle but with no bottom on it, turned upside down with a bung stuffed in to hold the liquid in, with these electrodes stuck through the bung, so you can connect your power supply down here to drive a current this way through the solution, meaning driving electrons that way through the solution. Where electrons go into the solution, they are going to join with something that is currently positively charged and to turn it to an atom. Hydrogen is going to pick up an electron from the electrode and go from being bonded with, no, not hydrogen, sodium ions in the solution are going to pick up electrons from the electrode to become sodium atoms, but sodium atoms don't hang around in water, they become sodium ions again, reacting with water to form sodium hydroxide, and that liberates hydrogen from the water, and the hydrogen bubbles will form on this graphite electrode and rise into this test tube, becoming trapped here, forming this bubble of hydrogen. At the other end, electrons are being taken out of solution into this graphite electrode and this way through the circuit. They are coming off something that is negatively charged, a chloride ion, which turns it into a chlorine atom, which forms into Cl2, chlorine gas, and rises up here. The student made an error in selecting the apparatus for this investigation. Okay, how should the apparatus be changed? Give one reason for your answer. Well, graphite doesn't dissolve in salt water, so that's not a problem. Should be using measuring cylinders, not test tubes, so that he can measure the volume in each one. That would be a start. And personally, I'd like to see them farther apart in the solution and the measuring cylinders all the way down over the electrodes, so that gas can't rise from this spot here and get in through there with, you know, any chaotic currents that are going on in there, because it'll get heated. You're putting power through this narrow bit of water here, bit of solution here. It's going to get warm. There are going to be currents that could cause bubbles to go into the opposite tracks. Mixing hydrogen and chlorine gases is an interesting proposition. Another student used the correct apparatus. Nice. Doesn't tell you. This student measured the volume of gases collected every minute for 20 minutes. Okay. We have a straight line for hydrogen rising from the origin. We have a line for chlorine that comes from the origin but takes a while to get going and then becomes a straight line. You are about to be asked why the difference. The difference is that chlorine is soluble. Describe the trends shown, use values. Oh, dear me. Volume of hydrogen collected increases at constant rate of 9 divided by 20. Yeah, 9 cc's per 20 minutes. I mean, if you really want, you can go 9 divided by 20 is and call it 0.45 cc's per minute. Chlorine, how would you describe it professionally? Chlorine collection lags, is initially very slow, then accelerates to, convenience, exactly the same, to the same rate. Lag behind for approximately 8 minutes, after which it is the same 0.45 cc's per minute, reaching 6.6 cc's after 20 minutes. Should be enough for 3 marks. Number of moles of each gas produced at the electrodes is the same. No gas escapes from the apparatus. Just at all, even though it was open. Absolutely none. No water evaporates as water vapour and escapes. Nothing. Suggests one reason why the difference... Yeah, chlorine is soluble. That'll do. Calculate the amount in moles of chlorine collected after 20 minutes. Use figure 8. For this, you are going to have to know something. You're going to have to... Oh, look, it tells you the volume of 1 mole of gas at room temperature and pressure. It's nice that this was at room temperature and pressure, isn't it? 24 cubic decimeters. A decimeter is a tenth of a meter, 10 centimeters. A 10 centimeter cube, a cubic decimeter, is 1 litre. So, if your answer in standard form, moles of chlorine. Standard form is a way of presenting numbers you may have seen. It's like 3.986 times 10 to the 14 cubic meters per square second is the GM of Earth. Or 1.51 times 10 to the 11 meters is the Earth's distance from the Sun at aphelion. That kind of format. So what we're looking at here is moles of chlorine. I did have this number, but I didn't know it was coming. 6.6, yes. 6.6, the chlorine of the beast. Right. There were 6.6 cc's, and 1 cc is 1 milliliter, so divide by 1000, you get 0.0066 litres of chlorine. There are 24 litres of chlorine per, if you prefer, centimetres to decimeters. A centimetre is 1/100th of a metre, a decimetre is 1/10th of a metre, so obviously a centimetre is 1/10th of a decimetre, so 1 decimetre is going to be 10 by 10 by 10 centimetres. So a cubic decimetre is 1000 cubic centimetres. Exact same thing. We have 0.0066 litres, there are 24 litres to a mole. If we divide 0.0066 by 24, we get 0.000275 moles of chlorine. But they want it in standard form, so that is 2.75 times 10 to the negative, because we're moving the decimal point to the right, 1, 2, 3, 4. 2.75 times 10 to the negative 4. Turn over for the next question and start a new video, because this is approaching 29 minutes. Name the product's form when chlorine reacts with potassium iodide solution. Potassium hydroxide and... no, potassium chloride and iodine. Potassium chloride and iodine. Explain why chlorine is more reactive than iodine. Because it's more electronegative, because it's more up this way. Because the outermost shell of chlorine is smaller and closer to the nucleus than that of iodine, therefore there's more energy released by completing it. Explain why hydrogen chloride is a gas at room temperature. Next.